Elon Musk's first principles reputation didn't start with rockets. It started with something much less glamorous: money moving between computers. In the late 1990s and early 2000s, the internet was still new enough that basic infrastructure, payments, identity, fraud prevention, security, was being invented in real time. That environment rewards a certain kind of thinking. You can't rely on tradition because tradition barely exists. You have to ask, what is this problem, really? And then build the simplest working answer. First principles thinking is often described as reasoning by reducing something to its most fundamental truths, then building up from there. Most people reason by analogy. This looks like what company X did, so we should do something similar. First principles reasoning says, ignore what company X did. What must be true in reality? What are the constraints? What is physically possible? What is mathematically necessary? What is legally required? What is human nature likely to do? Then you engineer a solution from those basics. Musk's early path forced him into that mindset. The PayPal story is frequently summarized as he co-founded a company that merged into PayPal, and then he used the money to fund space and clean energy ventures. That's accurate, but it skips the more important part. PayPal's world is a masterclass in constraints. You can't vibe your way into moving money online at scale. You either solve the system or the system breaks you. 1. The problem beneath the problem. Payments is not a product, it's a trust machine. At first glance, digital payments looks like a simple feature. You enter card details, money goes from A to B, done. In practice, payments is a multi-layer trust machine. Identity, who is the user and how sure are you? Authorization, are they allowed to spend this money? Settlement, how does money actually transfer across banks and networks? Fraud, how do you prevent bad actors from exploiting the system? Disputes, what happens when someone claims a transaction is wrong? Regulation, what rules apply and how do you comply at scale? A first principles approach begins by stripping away the product label and seeing the core physics. People will attempt to exploit any system that moves value. Therefore, the system must assume adversarial behavior. That single truth changes everything about design. It's not a checkout feature, it's risk management encoded as software. This is the kind of thinking that later shows up in rockets and factories. Rockets explode not because of bad luck, but because the physics and constraints are unforgiving. Online payments fail not because the idea is wrong, but because real-world adversaries and real-world institutions do not care about your startup story. 2. Speed versus safety, the classic constraint trade-off. In tech, speed is often praised. Ship quickly, iterate, grow. In payments, speed is dangerous if it outruns risk controls. A first principles thinker doesn't choose speed or safety as slogans. They treat them as variables and search for a workable balance. You can infer a Musk-like framework here. Define the objective precisely: fast transactions with low friction. Define non-negotiables: legal compliance, solvency, and fraud control. List constraints: bank rails, card networks, KYC, AML expectations, dispute processes, latency, and human behavior. Then engineer a solution from those basics. This method becomes obvious later in SpaceX. Designed to satisfy the fundamental constraints: orbital mechanics, materials, safety margins, cost. Then optimize the biggest cost drivers and failure points. 3. The obsession with bottlenecks begins here. A hallmark of Musk's style is his fixation on bottlenecks. First principles reasoning often leads to a simple question: what is the limiting factor? If you can identify the limiting factor, you can make disproportionate progress by solving it. In early payments, bottlenecks are usually fraud losses, chargebacks, user onboarding friction, bank settlement delays, scaling reliability. If fraud is your limiting factor, you don't fix it by polishing the UI, you fix it by building better risk models, tightening verification, and redesigning the system so exploitation is harder. If onboarding friction is your limiting factor, you don't accept slower growth, you redesign onboarding to be fast while still meeting regulatory expectations. Musk's later factory as product mindset can be seen as an extension of bottleneck logic. If production is the bottleneck, then production engineering is the product. 4. The intellectual stance. Assume the book is wrong until proven right. First principles thinking includes an attitude. You are willing to question accepted practices, not because you want to be contrarian, but because many best practices are just habits that survived long enough to look official. In financial systems, there are enormous inherited assumptions, legacy software architectures, rigid operational processes, security models built for older threats, organizational silos. A founder with first principles instincts looks at the whole pile and says which parts are fundamentally required and which parts are historically convenient. That's not a comfortable approach in a heavily regulated environment, but it can create breakthroughs if you respect the non-negotiables while challenging the rest. This also hints at a key Musk trait: high tolerance for complexity when complexity is necessary, combined with low tolerance for complexity when it's optional. That sounds contradictory, but it's actually how great systems get built. Necessary complexity, dealing with fraud, compliance, bank rails. Optional complexity, procedures that exist mainly because we've always done it that way. 5. PayPal as training for later industries. The stack becomes the battlefield. One of Musk's recurring moves is vertical integration. Build more of the stack yourself. In payments, you may start with third-party components, but at scale, you learn that outsourcing critical infrastructure can become your biggest risk. First principles thinking nudges you towards control of critical variables. If a component is strategically important and unreliable, internalize it. If a component is stable and commoditized, outsource it. SpaceX later internalizes manufacturing and design for many key parts, while still using suppliers strategically. Tesla internalizes battery and software components where they matter most. The pattern is similar. Own the variables that determine your cost, quality, and speed. PayPal's world teaches the lesson: if you don't control key parts of your system, someone else controls your destiny. 6. The psychological ingredient. Intensity as a method, not a personality quirk. People often describe Musk as intense, demanding, sometimes difficult. Whether one agrees or not, it's important to understand how intensity fits into a first principles approach. If you truly believe the system can be redesigned from fundamentals, you also believe that many delays are not natural laws, many constraints are negotiable, and many impossible tasks are simply unattempted. That belief produces urgency. The first principles thinker sees time as the enemy because every day you delay is a day the system's inertia reasserts itself. In payments, inertia is not just internal, it's the industry, the regulators, and the banks. So you push, you compress timelines, you ask why something takes months instead of weeks. You refuse the answer, that's how it's done, unless it's backed by a real constraint. This habit becomes extreme later in rockets, but it starts in the simpler world of internet infrastructure, a place where the constraint isn't physics, it's institutional inertia and adversarial behavior. 7. The payoff. From early exit to a bigger arena. When PayPal succeeded, Musk didn't just get money, he got proof that hard systems can be built, experience in scaling under pressure, and understanding that boring infrastructure is where leverage lives, and confidence that fundamentals can beat tradition. A typical founder might take that win and do another internet startup. Musk's next move was irrational by analogy and rational by first principles. By analogy, you invest in safer, familiar tech. By first principles, you ask, what are the biggest problems worth solving? What are the constraints that make them expensive? And can those constraints be reduced by redesigning from scratch? This is the hinge point. PayPal funds SpaceX and Tesla-era thinking, but it also forms the mental model. Systems are rebuildable. Once you believe that, the world looks different. You stop seeing industries as fixed structures and start seeing them as piles of assumptions waiting to be challenged. That sets the stage for SpaceX.
If PayPal taught Musk how to build systems under adversarial pressure, SpaceX forced his thinking into a stricter arena: physical reality. You can argue with bankers and regulators. You cannot argue with orbital mechanics. In spaceflight, the first principles approach is not a productivity hack, it's survival. Either you obey the fundamentals or you fail. SpaceX's founding story is often simplified into a heroic narrative. Musk wanted cheaper rockets, so he built a rocket company. But the underlying logic is more technical and more revealing. The first principles move here is not be bold. It is identify the real cost drivers, strip away inherited assumptions, and rebuild the process so cost and reliability improve together. 1. The core first principles question: what is a rocket made of and what should it cost? Traditional rocket development is expensive, slow, and dominated by aerospace contractors with long timelines. By analogy, a new company should either accept the price and buy launches, or become a subcontractor, or avoid the field entirely. A first principles thinker asks something else. What are the raw materials and components of a rocket? What does it fundamentally require to reach orbit? Why is it priced as if it's made of rare minerals and wizardry? Which costs are physics and which costs are process? This leads to a startling perspective. A rocket is largely aluminum, steel, composites, wiring, valves, pumps, and fuel. The raw materials cost far less than the final price. The gap is explained by specialized labor, low production volume, complex testing requirements, risk management, legacy procurement structures, mission assurance processes, and, importantly, lack of reuse. First principles doesn't mean ignoring safety or quality. It means separating necessary cost from cultural cost. The moment you believe much of the price is cultural, organizational, historical, procedural, you start looking for a new operating system for rocket building. 2. The physics-first discipline. Constraints become design inputs. To build a rocket, you don't begin with branding. You begin with constraints. Required delta V to reach orbit, mass fraction, engine efficiency, structural strength, thermal margins, guidance and control, failure modes, manufacturing tolerances. This is where Musk's thinking style gets sharper. The method is often described in steps like make the requirements less dumb, delete parts or processes, simplify and optimize, accelerate cycle time, automate. Whether or not you agree with the phrasing, the logic is pure first principles. Requirements are where hidden assumptions live. If you accept requirements without scrutiny, you build an expensive machine. If you challenge requirements, you may discover that half the complexity was self-inflicted. Example mindset. If a component exists because it always existed, question it. If a process takes 6 months, ask what constraint makes it take 6 months. If the answer is approval, ask what risk that approval is mitigating. If the risk is real, design a better mitigation. If the risk is historical habit, remove it. SpaceX's early years were brutal because rocket development is not forgiving. But first principles thinking is most visible when the stakes are high and the constraints are real. 3. Why vertical integration matters more in rockets than in most industries. In many industries, outsourcing is efficient. In rockets, outsourcing can multiply costs and slow iteration. The reason is fundamental. The product is complex and learning cycles matter. If you outsource key subsystems, you get slower feedback loops, more coordination overhead, higher unit costs, less design freedom, and a diluted understanding of failure modes. First principles logic says, if rapid iteration is your path to reliability and lower cost, you must control the learning loop. That naturally pushes you toward building in-house. SpaceX became known for doing a lot internally: structures, engines, avionics, software, integration. Not because outsourcing is bad, but because controlling the loop is a competitive advantage when complexity is high. This is the key. First principles is not only about ideas, it's about learning velocity. The faster you can test, fail, and fix, the faster you can approach reliability and lower cost. 5. Iteration as a weapon, treating failure as data without glorifying it. People sometimes misunderstand SpaceX's iteration culture as move fast and break things. That slogan doesn't belong in aerospace.
Rockets are expensive and failure has real consequences, but first principles thinking reframes the role of failure. A rocket test program is a discovery process. The question is not, will there be surprises? The question is, how quickly can we identify and remove surprises? If you slow down to avoid all failure, you risk learning too slowly and spending too much. If you rush recklessly, you learn in the most expensive way possible. The first principles approach attempts to keep the learning loop efficient, test components aggressively, instrument everything, analyze failures ruthlessly, redesign quickly, retest. Notice the word ruthlessly doesn't mean emotionally, it means methodically. You don't protect egos, you protect the mission by letting the data be the boss. 5. Reusability, the first principles insight that changes the cost curve. The biggest structural change SpaceX pursued was reusability. Traditional launches treated rockets like disposable items. By analogy, that's just how it is. By first principles, it's absurd. If planes were thrown away after each flight, air travel would be rare and expensive. But reusability has its own constraints: additional mass for landing gear and fuel reserve, thermal and structural stress, refurbishment time, engine relight requirements, guidance and control. The genius is not deciding to reuse, it is engineering a system where reuse is economically dominant. First principles thinking insists on the full equation. How many reuses are needed to beat expendable economics? Which refurbishment steps are unavoidable? Where is the real cost? Hardware, labor, or downtime? Which parts must be redesigned for rapid turnaround? This looks very similar to a software mindset, but applied to hardware. You want repeatable operations and predictable maintenance, not artisanal heroics. The deeper first principles insight is that reusability isn't a feature, it's an operating model. 6. The cost per kilogram to orbit lens simplify the goal. One reason Musk's thinking resonates is that he often reduces complex debates to a measurable objective. In rockets, that objective is something like cost per kilogram to orbit or cost per launch with reliability. Once you have a clear metric, you can evaluate every decision against it. Does this part reduce cost or increase reliability per unit? Does this process prevent a real failure mode? Does this supplier structure slow iteration? Does this design create a refurbishment bottleneck? First principles thinking loves metrics because metrics expose hidden assumptions. If someone argues for a complex process, you can ask, show how it changes the risk curve. If someone argues for an expensive part, you can ask, show how it affects mass fraction or reliability. This isn't about being cold, it's about being honest. Rockets don't care about narratives. They care about mass, energy, and margins. 7. Leadership in a first principles culture. Questions are the management tool. In a first principles environment, the leader's role is not to have every answer. The leader's role is to ask the questions that force reality to surface. What is the constraint here? What would happen if we removed this step? What is the failure mode we're guarding against? Is this requirement real or inherited? If we had to cut the cost by 50%, what would we do first? What would we do if we had to ship in half the time? These questions can feel uncomfortable because they challenge the legitimacy of accepted expertise. But when done well, they are not disrespectful, they are clarifying. The point isn't to embarrass engineers. The point is to prevent the organization from drifting into comfortable traditions. SpaceX's early identity was built on this. Do not worship the way aerospace has always done it. Worship the physics and the data. 8. The deeper philosophy. Transform impossibility into a sequence of solvable steps. The public hears colonize Mars and labels it fantasy. First principles thinking doesn't argue about vibes, it decomposes the impossible into sub-problems. How do you lower cost per ton to orbit? How do you build a reliable, reusable booster? How do you increase launch cadence? How do you manage life support, radiation, and logistics? How do you build propellant on Mars? Even if you think the final vision is too ambitious, the method is practical. If a goal is huge, you don't debate it abstractly. You break it into solvable steps, then attack the step that unlocks the next ones. This is how Musk bridges PayPal to SpaceX. It's not money to rockets, it's systems thinking to physics systems. The same mental muscle, rebuilding from fundamentals, just moved into a harder domain.
By the time SpaceX began landing boosters and raising launch cadence, Musk's first principles approach had become more than a personal thinking style. It had become an organizational operating system. To understand how he thinks, it helps to treat first principles not as a slogan, but as a repeatable playbook, a sequence of moves that show up again and again. This part lays out that playbook in practical terms, using SpaceX as the main example while showing how the same logic translates to any high-stakes, high-complexity project. 1. Start with a clear objective and a truth table of constraints. Most projects fail because objectives are fuzzy. First principles thinking begins with clarity. What are we trying to maximize? What are we trying to minimize? What constraints cannot be violated? For SpaceX, objectives often reduce to lower cost per launch, increase reliability, increase cadence, enable reusability, eventually expand capability. Then comes a truth table. Physics constraints, delta V, mass fraction, engine performance, material constraints, strength, temperature, fatigue, manufacturing constraints, tolerances, supply chain, operational constraints, turnaround time, weather, range safety, financial constraints, cash flow, development cost, human constraints, training, error rates, organizational load. The key is that constraints are treated as real objects, not as excuses. If something is a true constraint, you design around it. If it is not a true constraint, you eliminate it. This is a powerful mental filter. It prevents teams from confusing what we do with what must be done. 2. Question requirements first because requirements create hidden cost. Musk's approach is famously hostile to bloated requirements. In complex engineering, requirements can multiply until the system becomes expensive and fragile. Each requirement adds more components, more interfaces, more failure modes, more testing, more documentation, more delays. First principles thinking asks, why is this requirement here? What failure mode does it prevent? What evidence supports it? Is there a simpler way to mitigate the risk? This is not anti-safety, it is anti-unexamined bureaucracy. The result is a culture where engineers must defend complexity with evidence, not with tradition. In SpaceX terms, if an additional layer of redundancy is required, it must be tied to a failure mode analysis and reliability target, not to industry practice. 3. Delete before you optimize. Subtraction is a superpower. A common mistake in engineering is to optimize a system that shouldn't exist in its current form. First principles thinking often emphasizes deletion. Can we remove this part? Can we remove this step? Can we remove this interface? Removing things improves reliability, fewer parts to fail, cost, less material and labor, speed, fewer steps, and understandability. Simpler systems are easier to debug. SpaceX's learning here is instructive. A reusable rocket is already difficult. If your baseline design is cluttered with unnecessary complexity, reusability becomes even harder. Deletion is how you keep the challenge within human and organizational limits. 4. Simplify and standardize. Make the system predictable. After deletion, the next move is simplification and standardization. First principles thinking loves repeatability because repeatability reduces variance, and variance is the enemy of reliability. Standardize parts where possible, standardize procedures, reduce custom one-off processes, turn operations into routines. This is how aerospace becomes more like manufacturing. It's also why Musk often talks as if rockets are production items rather than projects. Projects encourage custom solutions. Production encourages stable processes. A key insight: you can't iterate fast if every iteration is a custom art piece. You need a stable base. 5. Tight feedback loops. The organization must learn faster than reality punishes it. SpaceX operates in a domain where reality punishes mistakes harshly. First principles thinking responds with a learning obsession. Instrument systems heavily, test frequently, review failures deeply, shorten the distance between design and test, ship improvements quickly. The goal is to make the organization's learning loop faster than the problem's complexity. If learning is slow, complexity wins. If learning is fast, you gradually conquer complexity. This is the deep connection between PayPal and SpaceX. PayPal's adversaries are fraud and systemic risk. SpaceX's adversaries are physics and engineering uncertainty. In both cases, you win by learning quickly and building systems that reduce vulnerability. 6. Focus on the biggest cost driver, not the loudest debate. A first principles thinker hunts for the dominant term in the equation. If you want cheaper access to space, what is the dominant cost driver? Historically, big drivers included expensive engines and hardware, low flight rate, no scale, expendability, no reuse, lengthy refurbishment, overly cautious processes not aligned with data, supply chain inefficiencies. You can argue about dozens of details, but the dominant terms are where leverage lives. Musk's style is to push teams towards leverage points, sometimes aggressively. If we solve this, everything changes. If we don't solve this, nothing else matters. It's an equation mindset applied to organizations. Maximize impact per unit effort. 7. Treat the factory and operations as part of the product. This might be the most misunderstood Musk idea. Many people think a company's product is the thing it sells. Musk often acts as if the product is the entire system that produces the thing. For SpaceX, the product is not only the rocket. It is design tools, manufacturing lines, test stands, launch procedures, refurbishment processes, software and telemetry, and the culture that makes iteration possible. First principles reasoning makes this obvious. If the objective is lower cost and higher cadence, then manufacturing and operations are not support functions. They are core engineering. This is why cadence matters so much. High cadence forces the system to become efficient because inefficiency shows up as delays and cost. 9. A specific thinking habit. Turn because into therefore. A simple way to see Musk's first principle style is to watch how explanations are structured. Analogy reasoning, we do X because everyone does X. First principles reasoning, we do X because Y is true, therefore X follows. That therefore is crucial. It forces logic, it forces causality, it exposes weak arguments. If someone can't complete the chain from truth to action, the action is suspect. SpaceX's environment is perfect for this habit because causality is measurable. If mass increases, performance changes. If engine reliability improves, mission reliability changes. If turnaround time drops, cadence rises. If cadence rises, unit cost drops through reuse and learning. When a leader insists on causal reasoning, organizations become less political and more engineering-driven, at least in theory. In practice, it's hard because humans are humans, but the method pushes the culture in that direction. 9. The emotional paradox, extreme vision versus brutal realism. Musk is associated with enormous visions: Mars, reusable rockets, rapid expansion. First principles thinking explains how that's possible without becoming pure fantasy. The vision is large and emotionally motivating. The execution is brutally grounded in constraints and step-by-step decomposition. This is the paradox that makes people either admire him or dislike him. He can talk like a dreamer and operate like a ruthless engineer. First principles is the bridge between those modes. It converts dream-scale goals into constraint-scale tasks. 10. How to apply this yourself. a practical first principles checklist. If you want how he thinks as something you can use, here's a practical checklist modeled on the pattern. Name the goal in one sentence. If you can't, you don't have a goal. List constraints in categories: physical or technical, legal, operational, human. Identify assumptions disguised as facts. Mark them clearly. Ask what must be true for success, not what's usual, what's necessary. Find the dominant bottleneck, the variable that limits progress. Delete steps, parts, processes that don't defend against a real constraint. Simplify what remains. Reduce interfaces and custom logic. Build a fast learning loop. Test, instrument, review, iterate. Measure with a small set of metrics tied to the goal. Repeat relentlessly, because first principles isn't one insight, it's a habit. Closing thought. First principles isn't a personality, it's a discipline. People talk about Musk's first principles thinking like it's a magic trait. It's more useful to see it as a discipline, a repeated choice to prioritize fundamental truths over inherited habits, and to build systems that learn quickly. PayPal trained him to respect adversarial reality. SpaceX.
If first principles is the slogan, engines are where the slogan either becomes engineering or becomes a myth. A rocket engine doesn't care about charisma, timelines, or ambition. It cares about temperatures, pressures, vibration modes, combustion stability, material fatigue, turbo pump dynamics, injector geometry, and countless small interfaces that can cascade into failure. In this domain, first principles thinking is not a motivational poster. It is a way of forcing the team to see what reality will actually allow, and then designing inside that box with relentless creativity. SpaceX's approach to engines shows a pattern Musk uses repeatedly. When the dominant cost or reliability driver is a subsystem, the subsystem stops being a part and becomes the center of strategy. That's why SpaceX didn't treat engines as a purchased commodity. The engine became a core capability, a lever that controls performance, costs, and iteration speed. 1. The first principles question. What does an engine need to do fundamentally? At its simplest, a rocket engine must combine propellant and oxidizer, ignite reliably, control the burn rate, generate thrust efficiently, maintain stability under extreme thermal and mechanical stress, and do it repeatedly without catastrophic failure. Everything else, specific cycles, architectures, supplier choices, are options. A first principles approach starts by writing down the non-negotiables and asking which design choices maximize reliability, manufacturability, and cost-effectiveness under these constraints. Traditional aerospace often optimizes for peak performance with low flight rates and high safety margins because the economic model supports it. Few launches, high price, extensive paperwork, and bespoke processes. SpaceX's economic model pushes the opposite direction: high cadence, reuse, and learning-driven reliability. That shift changes how you think about trade-offs. 2. Why good enough performance can beat maximum performance. A common misconception is that first principles always aims for the most advanced, highest performance solution. In reality, it often aims for the solution that best fits the objective function. If your objective is lower cost per flight and higher cadence, then maximum theoretical performance may be less important than simpler manufacturing, robust operation, easier refurbishment, stable supply chains, predictable behavior across many flights. This mindset appears across Musk's projects, not best in the abstract, but best under the chosen mission. The first principles move is to define the mission mathematically and then choose what's optimal inside that definition. 3. The obsession with margins. Everything has a budget. In rocketry, margins are life. You have mass margins, thermal margins, structural margins, performance margins, schedule margins, and financial margins.
First principles thinking treats these as budgets. A budget forces choices. If you spend too much mass on one area, you must save mass elsewhere. If you add redundancy, you pay in weight or complexity. If you demand extreme performance, you pay in fragility, testing, or cost. Musk-style reasoning often sounds like, if we add this, what margin does it consume? Where do we get that margin back? Is the margin consumption real, or can we redesign? That constant balancing act is why first principles isn't just ask why 5 times, it's an accounting system for reality. 4. Combustion stability, the hidden dragon. One of the hardest things in rocket engines is combustion stability, keeping the burn smooth rather than oscillatory. Instabilities can destroy hardware quickly. The first principles way to approach instability is not to blame luck, it is to treat the engine as a coupled dynamic system: fluid flow, acoustic modes, injector dynamics, chamber geometry, thermal gradients, and control responses. A team that thinks in first principles terms will ask, what physical mechanism causes the oscillation? Which parameters control the mechanism? What design changes damp it? What measurement can reveal it early? This is also where Musk's focus on instrumentation matters. If you can't measure something, you can't control it. SpaceX invested heavily in test infrastructure because the first principles logic is simple. Knowledge comes from reality, not from consensus. 5. Reusability changes the engine's job description. If an engine is used once, you accept certain wear patterns and maintenance assumptions. If an engine is used repeatedly, the constraints change. Thermal cycling becomes dominant, fatigue accumulates, inspection must be faster, refurbishment must be repeatable, parts must be designed for operational stability. First principles reasoning here is brutal. If refurbishment requires artisanal heroics, reuse fails economically. Therefore, the engine must be designed not only for thrust and efficiency, but for operations. This is the key. Musk tends to collapse the boundary between design and operations. In traditional organizations, design is one department and operations is another. In a first principles system, you treat them as one integrated loop. If a design causes operational pain, it's not operations problem, it's a design flaw. 6. The materials mindset. Treat materials as constraints and opportunities. Materials in rockets face cryogenic temperatures, high-temperature exhaust, vibration and acoustic loads, oxidation, fatigue, and stress concentrations. First principles thinking asks, what must the material do? Then it explores which alloys or composites satisfy the need, how to manufacture them repeatably, how to inspect them, how they behave across many cycles. A subtle Musk-like pattern is this. He tends to distrust specialness. If a material is rare, expensive, or difficult to source, it creates supply chain fragility. If a process requires a niche provider, it slows iteration. So the team is pushed towards solutions that can scale industrially. That doesn't mean cheap in the naive sense. It means scalable. If your long-term goal is high cadence, your materials and processes must be compatible with volume. 7. The supply chain as physics. Lead time is a constraint like gravity. People think first principles is about physics, but in real engineering, supply chain constraints behave like physics. If a critical part has a 40-week lead time, your iteration loop becomes slow. Slow learning means slow reliability improvements. That's a real constraint. So a first principles leader asks, can we make this part ourselves? Can we redesign to use a different part? Can we standardize components across systems? Can we reduce the number of unique parts? SpaceX's make versus buy decisions often reflect this, not ideology, constraint management. The mission is faster learning, and faster learning requires removing lead time bottlenecks. 9. The test until it's boring philosophy. One reason SpaceX is associated with rapid progress is the bias towards testing. A first principles view of testing is not be safe. It is, if the system is complex, the number of unknowns is high. Unknowns create risk, and risk must be reduced with data. Data comes from tests that resemble reality. Testing can look expensive, but it is often cheaper than slow development combined with surprise failures late in the program. This is another consistent Musk pattern. Pay early to reduce unknowns, or pay later with compounded cost and schedule slips. 10. Failure analysis turns emotion into mechanics. When a failure happens, a first principles organization tries to remove moral judgment and replace it with causal analysis. What exactly happened? What chain of events led to it? What design or process allowed the chain? What change breaks the chain? This is hard because humans naturally react emotionally, but first principles thinking treats emotion as noise, not because people don't matter, but because reality won't negotiate. If you want to keep people safe and succeed, you must understand causality without defensiveness. 10. The 5-step compression of progress. Across Musk-led teams, a recurring rhythm appears. Define the requirement, then challenge it. Remove unnecessary parts and steps. Simplify what remains. Build a tight test loop and scale what works. Engines, materials, and margins are where this rhythm becomes visible. You can't fake improvements with marketing. The engine either runs or it doesn't. The structure either survives or it doesn't. The first principles approach becomes a kind of ruthless honesty. Show me the data, show me the mechanism, show me the constraint. The deeper takeaway, first principles is not about being clever, it's about being precise. Precise about what reality demands, and precise about where to apply effort. Reusability is often described as a technological breakthrough. Land the booster, fly again, reduce cost. That's true, but it's incomplete. The bigger transformation is organizational and operational. A reusable rocket is not just a rocket that lands. It is a rocket that belongs to a fleet, and a fleet is an operating system. Schedules, maintenance, quality control, logistics, training, inspections, and standardized procedures. First principles thinking is what forces the shift from launch project to flight operations. 1. The first principles argument for reuse is economic, not inspirational. A booster is an expensive machine. Throwing it away after a single use is like discarding an airplane after one flight. The first principles argument is simple. If the hardware is a large portion of the cost, and if the hardware can be recovered and reused safely, then the cost per flight can drop dramatically if refurbishment is efficient. The if is everything. A booster that lands but requires months of labor to refurbish is not a cost breakthrough. The first principles approach refuses to celebrate the landing alone. It asks, how many flights per booster are needed to amortize manufacturing cost? How much refurbishment labor is acceptable per flight? What inspection steps are truly required? Which parts drive turnaround time? What is the dominant bottleneck preventing rapid reuse? This is why reuse is an operating system. You're not inventing a trick, you're redesigning the economics of spaceflight. 2. Reuse forces you to treat time as a design parameter. In expendable rocketry, you can tolerate long integration and slow processes because the mission is singular. In reuse, your mission is repeated. That makes turnaround time a design parameter. First principles reasoning treats time like mass. You have a turnaround budget. Every inspection step consumes time. Every repair consumes time. Every manual procedure consumes time and introduces human error risk. So the design evolves toward easier access to components, fewer unique fasteners, modular subsystems, sensors that make inspections faster, materials and coatings that resist wear. This is an important Musk-style concept. If a process is slow, don't only work harder, redesign the system so the process is unnecessary or automated. 3. The hidden enemy is refurbishment complexity. Refurbishment is where many reused dreams die. It's easy to say, fly again. It's hard to make fly again routine. First principles thinking isolates refurbishment as a problem with fundamentals. What causes wear? What is the distribution of wear across flights? Which wear mechanisms are predictable versus stochastic? How can we design components so wear is benign? Can we monitor wear in flight so we reduce inspection uncertainty? If you can predict the health of the hardware, you can reduce inspection time. If you can reduce inspection time, you increase cadence. If you increase cadence, you reduce cost per flight. That chain is first principles applied to operations. 4. Reliability is not more rules, it's fewer unknowns. Traditional aerospace often increases reliability by adding more review boards, more paperwork, more sign-offs, more layers of approval. These can reduce risk, but they also slow learning and raise cost. SpaceX's first principles approach tends to bet on better instrumentation, better testing, better data analysis, and designs that are inherently robust. This is controversial in some circles because it shifts trust from procedure to feedback loops, but it's consistent with the fundamentals. Reliability improves when you understand failure modes. Understanding improves with data. Data improves with frequent tests and flights. A fleet gives you what a project can't: repeated exposure to reality. Each flight is a data point. The organization becomes a learning machine. 5. Cadence as a strategic weapon. A high launch cadence is not only about revenue, it is about learning rate. In complex systems, you can think of progress as progress per iteration times iterations per year. If you increase iterations per year, you can improve faster even if each iteration is only modestly better. First principles thinking sees cadence as leverage because it compresses the feedback loop between design, manufacturing, and operations. This is a recurring Musk theme. Speed is not a virtue by itself. Speed is a method to generate learning. Learning is the input to reliability and cost reduction. 6. Standardization, the quiet hero of reuse. To run a fleet, you need standard processes. If every booster is unique, your maintenance becomes custom, your documentation grows, and your training load explodes. Standardization reduces variance. Standardized hardware configurations, standardized checklists, standardized refurbishment steps, standardized sensor packages. First principles thinking values standardization because variance produces unknowns, and unknowns produce risk. A fleet that behaves predictably is a fleet you can scale. This also ties to Musk's delete and simplify philosophy. Standardization is simplification at the organizational level. It means fewer exceptions. Fewer exceptions means fewer surprises. 7. The factory plus operations plus design triangle. Reusability forces all three to become one loop. Design chooses architectures and materials. Manufacturing builds hardware that must match design intent reliably. Operations flies, recovers, inspects, and refurbishes. Feedback from operations goes back to design and manufacturing. If the loop is slow, the system stagnates. If the loop is tight, the system improves rapidly. Musk's management style often pushes for this tight loop. He is known for wanting engineers to see the real hardware, be close to the manufacturing line, and understand operational pain points. The first principles logic is straightforward. You can't optimize what you don't experience. 8. Risk becomes quantifiable when you have a fleet. In a one-off project, risk assessment is partly theoretical. In a fleet, you get statistics. How often a component fails, how performance drifts over time, what conditions correlate with anomalies. First principles thinking loves quantification because it reduces debate. If someone insists on an expensive procedure, you can ask, what data supports it? What risk does it reduce? Can we reduce the same risk more efficiently?
This is where the cultural shift happens. Decisions become less about tradition and more about evidence. 9. The real meaning of rapid reuse. When people hear rapid reuse, they imagine quick turnaround. The first principles interpretation is deeper. Rapid reuse means the organization can treat flights as routine. That implies predictable hardware behavior, minimal refurbishment, streamlined logistics, stable supply of replacement parts, trained teams for repetition, automation where possible, and a culture that learns from anomalies without panic. It's not a miracle landing, it's the boring excellence of airline operations applied to rockets. The hard part is making it boring. 10. Why this thinking matters beyond rockets. The reuse operating system illustrates a general Musk pattern. Don't optimize the thing alone, optimize the system that produces the thing and operates the thing. If you apply that to business, it means don't optimize the product features alone, optimize manufacturing, distribution, support, and iteration loops. This is why Musk's first principles thinking often looks industrial. He treats companies as machines that transform inputs into outputs. The output might be software, cars, rockets, or satellites. The method is similar. Build a learning system, then scale it.
First principles thinking is usually presented as calm and rational. Reduce to fundamentals, build up logically. But in real life, especially in SpaceX's early years, the environment is not calm. There's schedule pressure, financial pressure, public scrutiny, and technical uncertainty. Under these conditions, most organizations revert to habit. They follow precedent because precedent feels safe. First principles thinking is harder under pressure, yet that's where it matters most. This final part looks at how Musk's first principles approach shows up in leadership decisions and organizational culture, especially when the stakes are high. 1. The reality filter, separating what feels true from what is true. A first principles leader tries to build a culture where claims must pass a reality filter. Is the claim measurable? Is the mechanism understood? Is the evidence direct or secondhand? Are we mistaking confidence for truth? In high complexity environments, people can sound plausible and still be wrong. Reality filters reduce the power of persuasive narratives and increase the power of data. That can create tension because it challenges status and authority, but it also creates progress because it prevents the organization from drifting into self-deception. Musk's style often appears as impatience with vague answers. That impatience is not merely temperament, it is the enforcement mechanism of the reality filter. It pushes the organization away from soft certainty and toward hard evidence. 2. Decision-making as constraint solving. Under pressure, decision-making can become emotional or political. First principles thinking reframes decisions as constraint solving. What options satisfy the constraint set? Which option maximizes the objective function? What are the failure modes of each option? What uncertainties dominate the outcome? This is why Musk is associated with aggressive timeline compression. He treats time as a constraint like any other. If the schedule is tight, he doesn't accept "we can't." He asks, which constraint makes it impossible? Can we change the constraint? Can we remove steps? Can we parallelize work? Can we redesign? Sometimes this produces breakthroughs. Sometimes it produces stress. The important point is the method. Assume there is a solution until the constraints prove otherwise. 3. The delete, simplify, accelerate loop as a cultural norm. First principles thinking becomes powerful when it becomes routine. In a Musk-style organization, people learn that complexity must be defended, requirements must be justified, and speed is a design variable. That creates a culture where engineers expect to be challenged. The challenge can be uncomfortable, but it can also prevent complacency. A key benefit, the organization becomes less likely to accumulate institutional sludge.
processes added over time that nobody questions. A key risk: if the challenge becomes performative rather than evidence-based, it can create burnout. The best version of this culture keeps the challenge anchored to the reality filter. The goal is not to pressure people, the goal is to pressure assumptions. 4. How first principles handles disagreement. In many organizations, disagreement is resolved by hierarchy or politics. In a first principles environment, the ideal resolution is: define the claim, define what evidence would settle it, run the test, accept the result. This is why testing and measurement are so culturally important. They are not only engineering tools, they are conflict resolution tools. If you can test, you can reduce argument. If you can't test, you get endless debate. Musk's approach often pushes teams toward "show me." That can feel harsh, but it has an internal logic. Evidence scales better than opinion. 5. The paradox of risk tolerance. SpaceX is often seen as risk-tolerant, but first principles thinking doesn't mean take more risk. It means identify risks precisely, prioritize them, and reduce the dominant risks with the highest leverage actions. In rocketry, some risks are unacceptable. The first principles approach is not to gamble, it is to move fast in areas where learning is valuable and risk is manageable, while being conservative where risk is catastrophic. This creates a nuanced picture: rapid iteration in prototypes and tests, high discipline where safety and mission-critical systems demand it. The method is not recklessness, it is targeted learning. 6. The role of narrative. Vision as fuel, fundamentals as steering. Musk uses big narratives: reusable rockets, Mars, multi-planetary future. Narratives energize teams and attract capital and talent, but narratives can also distort reality if they become substitutes for engineering. First principles thinking acts as steering. Vision provides direction, fundamentals provide control. The organization can dream, but it must build on physics. That combination is rare. Many organizations have vision without engineering discipline, or discipline without vision. The Musk model attempts to blend both. 7. Hardcore ownership. Responsibility as a first principles mechanism. Another cultural feature often associated with Musk-led teams is extreme ownership. In first principles terms, ownership reduces system entropy. If responsibility is vague, failures become someone else's problem. If responsibility is clear, the system can learn efficiently. Ownership also accelerates feedback loops. If you own a subsystem end to end, you see how design choices affect manufacturing and operations. That end-to-end visibility is essential for first principles optimization because it reveals hidden constraints and unintended consequences. 8. The difference between impossible and unattempted. One of Musk's most consistent behaviors is treating impossible as a hypothesis rather than a conclusion. First principles thinking asks, what makes it impossible? Is that a physical limit or a process limit? Are we mistaking never done before with cannot be done? What would be required to do it? This mindset can be inspiring, but it also raises expectations. It can compress timelines and increase pressure. In a healthy implementation, it creates innovation. In an unhealthy implementation, it can create exhaustion. The difference often lies in whether the organization truly deletes and simplifies, or whether it merely demands more effort. 9. The practical mental model, a ladder of reasoning. A useful way to summarize Musk's first principles approach is as a ladder. Objective: what are we trying to achieve? Constraints: what cannot be violated? Physics or mechanism: what is the causal story? Design: what architecture satisfies mechanism and constraints? Process: how do we build it reliably and repeatedly? Operations: how do we use it at high cadence? Feedback: how do we learn and improve quickly? This latter is why Musk's thinking is so systemic. He doesn't stop at idea or design, he pushes through to process, operations, and feedback. That's why first principles for him isn't a brainstorming technique, it's a complete organizational model. 10. Closing synthesis. PayPal to SpaceX as one continuous method. From PayPal to SpaceX, the industry changes, but the method stays consistent. At PayPal, the adversary is fraud, trust, and institutional constraints. At SpaceX, the adversary is physics, complexity, and high-stakes reliability. In both, identify the true constraints, challenge inherited assumptions, delete unnecessary complexity, build tight feedback loops, and scale what works. If you want the simplest takeaway, it's that Musk's first principles thinking is not merely think differently, it is a repeated insistence that the world is knowable through fundamentals, and that systems can be rebuilt if you're willing to face reality without comfort. That is why the PayPal exit becomes the seed of SpaceX, not because money magically buys rockets, but because the mental model, constraints, systems, learning loops, transfers. Once you see the world that way, industries look less like monuments and more like puzzles. And puzzles can be solved, one constraint at a time.
If SpaceX proved it could build rockets, Starlink proved it could build a system. Rockets are astonishing machines, but rockets are still a means. A reusable launcher is a cost reduction engine. A satellite network is a revenue and capability engine. In first principles terms, Starlink is a logical next step. Once you lower the cost of reaching orbit, you ask what valuable infrastructure becomes possible in orbit at scale. Starlink also reveals something important about Musk's first principles approach. It isn't limited to physics-heavy hardware. It extends naturally into networks, unit economics, and feedback-driven iteration. The method is consistent. Identify fundamental constraints, reduce cost drivers, build tight loops, and scale. 1. The first principles question: what is the actual job of global internet? Most discussions about internet access begin with analogy: build towers, lay fiber, partner with telecoms, follow established playbooks. Starlink begins with a first principles reframing. The job is not fiber or cell towers. The job is move data reliably to users everywhere with acceptable latency, price, and availability. Once you define the job, you can explore architectures. Fiber is fantastic, but expensive and slow to deploy in remote regions. Cellular infrastructure depends on dense tower networks and spectrum planning. Under a first principles lens, space becomes a candidate not because it's romantic, but because it may be the least bad solution under certain constraints. The fundamental constraints for global connectivity include geography, mountains, oceans, rural isolation, capital intensity, cost to build and maintain infrastructure, deployment speed, years versus months, regulatory complexity, permits, rights of way, and reliability under disasters. Space-based broadband becomes appealing when you treat the problem as how do we minimize infrastructure friction per connected user. 2. Latency as the key constraint. Why low Earth orbit matters. Satellite internet existed before Starlink, but it often relied on geostationary orbit, which has high latency due to distance. First principles thinking starts from physics. Speed of light is finite. Distance matters. Therefore, to reduce latency, satellites must be closer to Earth. That points to low Earth orbit, which demands many satellites to provide continuous coverage. Here, the first principles chain becomes LEO reduces latency, LEO requires large constellations require low-cost satellites and frequent launches require low cost per launch and high cadence. Reusability and mass production reduces cost per launch and per satellite. Starlink is therefore a systems-level strategy. Rockets, manufacturing, satellite design, ground terminals, software, and operations all integrated. It's vertical integration applied to a network. 3. The economics, from one-off satellites to a manufacturing product. Traditional satellites are expensive, custom-built machines. They're treated like spacecraft art pieces. First principles reasoning sees a different possibility. If you need thousands of satellites, custom designs are a bottleneck. Therefore, satellites must become mass-produced. Mass production changes everything. Design must be standardized, components must be sourced at scale, assembly lines must be optimized, testing must be fast but sufficient, failures must be detected early and cheaply, software updates must be robust, and the entire system must tolerate some level of attrition. This resembles how airlines operate fleets and how car makers produce vehicles. Musk's approach thrives in this environment because it treats manufacturing as the product. The same mindset that builds reusable boosters can build satellite assembly lines. The first principles move is again, turn a project into a factory. 4. The dominant bottleneck shifts from launch to terminals. In many tech projects, the bottleneck is misunderstood. People might assume Starlink's bottleneck is rockets, but first principles thinking insists you continually recheck the limiting factor. For a satellite internet network, major bottlenecks include satellite production capacity, launch cadence, ground infrastructure, gateways, spectrum coordination and regulation, and crucially, user terminals. The user terminal, the dish, is a physical product with electronics, phased array antennas, manufacturing complexity, and cost. If the terminal is too expensive, adoption stalls. If the terminal is cheap but unreliable, churn rises and support costs explode. So the first principles question becomes, what is the minimum terminal performance required? What antenna architecture meets that requirement? What cost target makes the service accessible? How do we manufacture at scale? This resembles Tesla's problem with batteries. The cost driver becomes the strategic focus. Musk's playbook is to focus intensely on the dominant cost driver until it bends. 5. Network effects meet aerospace. Cadence creates learning, creates cost reduction. Starlink's system benefits from a compounding loop. More satellites, better coverage and capacity, better coverage, more customers, more revenue, more ability to invest in launches and satellites, more launches, faster constellation growth and replacement, faster replacement, newer tech in orbit, better performance. This is a network flywheel. First principles thinking helps because it identifies which flywheel component is currently limiting growth and then attacks it with engineering focus. This is also where Musk's obsession with iteration shows up again. In a network, software and hardware can evolve rapidly. The constellation can be refreshed continually if launch cost is low and manufacturing is fast. Traditional satellites aim for long lifetimes because replacing them is expensive. Starlinks can evolve faster because the system is designed around replacement and upgrade cycles. The first principles insight: if replacement is cheap, evolution accelerates. 6. Reliability as a statistical property, designing for fleet behavior. A single satellite might be extremely reliable, but in a constellation of thousands, some failures are inevitable. First principles shifts the reliability concept from perfect components to robust system. Assume some satellites fail, assume some links degrade, assume some ground stations have outages. Design the network to reroute, adapt, and maintain service. This is similar to how the internet itself works. Redundancy and routing are built in. Starlink is an internet-like system in orbit. That means software-defined behavior, dynamic resource allocation, continuous monitoring, and rapid upgrades. Again, the pattern is build a system that learns and adapts, not a system that depends on perfection. 7. Regulatory constraints. First principles meets the political layer. Not all constraints are technical. Starlink operates in a world of spectrum rights, national regulations, and coordination with other satellite operators. A first principles approach doesn't ignore it, it treats it as another constraint set. If spectrum is required, obtain and coordinate. If national permission is needed, negotiate and comply. If interference risks exist, engineer mitigation and process. Musk's approach tends to move fast, which can clash with slow regulatory environments, but the first principles method is still applicable. Separate what is non-negotiable from what is habit. Non-negotiable, legal compliance in jurisdictions. Negotiable, speed of approvals through better documentation, partnerships, or phased deployment. The point is not to hack regulation, but to treat regulation as part of the system design. 9. Vertical integration again. Why SpaceX can do Starlink when others can't. A satellite broadband constellation is expensive because it requires rockets, satellites, ground terminals, ground networks, and software. Most companies would have to buy launches at market prices. SpaceX can launch itself at internal cost structures. That is a first principled advantage: reduce the cost of the biggest input. This is analogous to Tesla building its own battery supply and software stack. When you control the critical inputs, you can optimize the entire system rather than negotiate with constraints you can't change. 10. Starlink as strategic flexibility, redundancy against launch market cycles. There's another first principles benefit: resilience. The launch market can be cyclical. Commercial and government contracts vary. Starlink gives SpaceX an internal demand driver for launches and a recurring revenue stream. That reduces dependence on external customers. This is first principle strategy. Identify a major risk, external demand variability, build a system that reduces that risk, internal demand and recurring revenue, and ensure the system leverages your core advantage, launch cost and cadence. You might notice that Starlink follows the same patterns as SpaceX and Tesla. The method is consistent: build the loop, tighten the loop, scale the loop. Starlink is therefore not an extra project. It is the logical extension of SpaceX's first principles engine: reduce orbit cost, then build orbit infrastructure that generates value, which funds more cost reduction.
People often ask, how can I think like Elon Musk? That question usually gets answered with a slogan: think in first principles. But slogans don't help when you're facing a messy, real-world problem with politics, limited budgets, incomplete data, and human friction. The useful version of first principles is an operating manual, a sequence of moves you can apply repeatedly. This part breaks down Musk's pattern into a practical framework, one that explains why the approach works, where it can fail, and how it shows up in SpaceX-level decisions. 1. Step 0. Choose problems where fundamentals allow asymmetry. A hidden Musk move is problem selection. First principles thinking is powerful when the industry is burdened by inherited assumptions, costs are inflated by process rather than physics, and there is a clear path to learning-driven improvement. Spaceflight historically had all three. Launch costs were high partly due to low cadence and expendability. The assumption that rockets must be disposable was not a law of physics. It was a habit reinforced by economics and risk culture. So the first principles question becomes, is there a fundamental reason this must be expensive, or is it expensive because the system is built that way? Musk tends to pursue domains where the second answer is at least partly true. That's where a redesign can create asymmetry. 2. Reduce the problem to a physics statement, even if it's not physics. Even in non-physical domains, Musk tries to translate the problem into something like physics: a constraint equation, a cost equation, a throughput equation, a reliability equation. Examples: rockets, mass fraction, thrust, delta V, thermal loads. Manufacturing, cycle time, defect rates, throughput. Networks, latency, bandwidth, coverage, unit economics. Business, cash flow, pricing, margins, growth loops. This translation matters because it makes debates concrete. It forces the team to argue in terms of variables and mechanisms rather than preferences. A practical method: write the problem in one sentence. Write the success metric in one number or small set of numbers. List the variables that move that number. If you can't do this, you're not doing first principles, you're doing philosophy. 3. Attack requirements. Make the requirement less dumb. Requirements often contain hidden assumptions. Musk's approach is to treat every requirement as guilty until proven necessary. Ask, who wrote this requirement? What risk is it addressing? What evidence supports it? Can the requirement be replaced with a simpler constraint? This is the first place breakthroughs happen because many costs are self-inflicted. In a complex system, every additional requirement multiplies complexity, testing, and time. But the key is discipline. You can't remove requirements blindly. You need to connect each requirement to an actual failure mode. First principles thinking is not anti-safety, it is anti-unexamined complexity. 4. Delete. Subtraction beats cleverness. Musk's teams are often pushed to delete parts and processes. Deletion is powerful because fewer parts equal fewer failures. Fewer steps equal faster execution. Fewer interfaces equal less integration pain. A good deletion question: if we were forced to ship in half the time, what would we remove? If we were forced to cut cost by 50%, what would we remove? This exposes what is truly necessary versus what is comfortable. 5. Simplify. Reduce interfaces, standardize, and make it repeatable. After deletion, simplify. Simplification isn't just make it easy. It's reduce the number of unique components, reduce the number of custom procedures, design for manufacturing and servicing, and reduce variance. This is where first principles becomes industrial. Musk often treats simplicity as a moral virtue because it reduces unknowns. In systems engineering, unknowns create failure modes, so simplicity isn't aesthetic, it's reliability engineering. 6. Optimize only after simplification. Many organizations optimize too early. They polish a flawed architecture. Musk's approach is to delete, then simplify, then optimize. Optimization without simplification is often wasted. It makes the wrong thing slightly better. First principles thinking tries to make the right thing exist first. 7. Accelerate. Compress feedback loops, not just schedules. Speed is often misunderstood. Musk's style is not simply work faster, it is make learning faster. Put engineers close to hardware. Test frequently. Instrument everything. Review anomalies quickly. Fix and retest. This builds a learning machine. When learning is fast, improvement compounds. When learning is slow, complexity accumulates and morale erodes. A practical test. How long does it take to go from idea to prototype to test to data to redesign? That is your iteration loop. If your loop is slow, your progress will be slow no matter how smart you are. 8. Automate last, but plan for it. Musk is known for ambitious automation attempts, sometimes too early. The disciplined version of first principles says, automate once the process is stable, because automating a flawed process locks in flaws. But he also thinks ahead. Design parts and procedures so automation becomes easier later. Build data systems early. Standardize interfaces. In other words, you build the runway for automation, then take off when ready. 9. The proof culture. Opinions are cheap. Data is currency. First principles thinking requires a culture where claims must be testable, where disagreements are resolved by experiments, and where status doesn't override evidence. This is hard because humans love certainty, but it's how you avoid drifting into tradition. Musk's insistence on "show me the data" can feel intense, but it serves a function. It forces the organization to anchor decisions in reality. A practical habit: when someone proposes a solution, ask, what would convince us it's wrong? If you can't answer, you're not thinking scientifically. 10. Where first principles can fail: the human cost and the blind spots. To make this honest, first principles thinking has failure modes. Overcompression, timelines shrink faster than real constraints allow, leading to burnout. Requirement whiplash, constant questioning can destabilize teams if it feels arbitrary. Local optimization, focusing on one bottleneck can create new bottlenecks elsewhere. Underestimating soft constraints. Culture, regulation, and public trust can't be brute forced like physics. Leadership bottleneck. If too many decisions require the leader's approval, the leader becomes the constraint. A mature first principles organization builds systems so that the method scales beyond one person. Otherwise, the leader's intensity becomes the engine, and engines overheat. 11. The core insight. First principles is ultimately a method for escaping inherited reality. The world you inherit is full of assumptions. This industry is expensive. This timeline is normal. This is how it's done. This can't be changed. First principles thinking is a disciplined way of asking which of these statements are laws of nature, which are habits. SpaceX succeeded where many failed because it treated key cost drivers, launch costs, reusability, manufacturing cadence, as habits that could be changed, not as laws of physics. That's the PayPal to SpaceX arc. Move from digital trust systems to physical trust systems, but keep the same mental engine. 12. Final takeaway. How Musk's first principles thinking feels from the inside. From the inside, it likely feels less like philosophy and more like constant pressure to justify everything. Why this part? Why this process? Why this timeline? What is the mechanism? What is the bottleneck? What does the data say? That can be exhausting, but it can also be liberating because it means you're allowed to redesign the world rather than accept it. And that, ultimately, is why the phrase first principles sticks to Musk. Not because he invented it, but because he operationalized it at scale, turning it into a machine that converts ambition into engineering steps and engineering steps into systems that fly. If you want to use it yourself, start small. Pick one problem, define the objective, list constraints, challenge requirements, delete and simplify, build a fast test loop. Do that repeatedly, and you'll be doing the real thing, not the slogan.